Okay, and we're going to have Akio Gaule from the O3DE engine talk about Vulkan synchronization. Please give them a warm welcome.
Hello, everybody, and welcome to Mastering Chaos, Navigating Vulkan Synchronization on O3DE engine. Full disclosure, that title was generated using ChatGPT, by the way. So synchronization is one of the most complex subjects on Vulkan, or at least it was for me. And sometimes we need a more practical view on how those concepts translate from the theory into a real world application. So in this talk, I'm going to go through O3DE's approach on resource synchronization and how the data collected from the users go through O3DE's rendering pipeline into the GPU in order to produce the expected result. So who am I? My name is Akio. I'm a graphics engineer working in O3DE. I've been involved since the early beginnings of the engine before it was even called O3DE. And I focus mainly in everything to do with Vulkan on O3DE. So let's go through the agenda. First, I'm going to go through an overview of O3DE that's going to help us understand how the resource management it's implemented. And then I'm going to go through the next three topics there. They basically encapsulate the way O3DE handles producing a frame. We have three phases. The first one is the prepare phase, is where we collect all the necessary data. Then we have a phase that we call the compile phase, where we grab that data and we process it in order to produce the synchronization that we need. And finally, we have the execution, where we submit the actual word into the command list and the queues that we need. So what is O3DE? I don't know how many people here know what O3DE is, but O3DE is an open source real-time multi-platform 3D engine that is part of the Linux Foundation. You can use it for building your games, simulation, robotics, VR experience, all that kind of stuff. It has most of the bells and whistles as other engines out there, like PBR rendering, global illumination, ray tracing, animation, particle, all that kind of stuff. You can use this as is. Basically, you go and download it and start using it, or you can modify it in any way you want. But if you do something cool, we encourage people to contribute back to the repository. It supports multiple rendering APIs, Vulkan, of course, also DX12 and Metal, and it runs in multiple platforms, Linux, Windows, iOS, macOS, and Android. So O3DE's graphic engine that is called Atom has two main components. Atom was designed for modern APIs like Vulkan and DX12. So we have the application that it could be the game talking to the first component that we call the rendering pipeline interface. The RPI is one of the core systems that drives all the rendering. This is where most of the graphics features live. This is where we have the pipeline system, the path system, the scene lives there. The features like the shadowing, lighting, skybox, all lives in this component. Then we have the render hardware interface, or RHI. This is where all the cool stuff happens. This is where I do most of my work. The RHI is the way that the RPI communicates with the device. The RHI is an agnostic interface that is used to create all the resources like buffer images, buffer views, shader models, and all that kind of stuff. The RHI has a multiple implementation for all of the rendering APIs it supports. So there's one for Vulkan, another for Metal, another one for DX12. And this is where all the Vulkan code lives. So if you take a look at that image, that looks pretty simple, just a shaderable material, some skybox and a terrain, and some shadow and lighting. But in order to produce that image, we have more than 50 passes that are necessary to produce the result. So we have dozens of resources that are being shared between those passes in order to produce that image. That's why I call it like synchronous chaos, because there's a lot of things that need to go right in order to produce the image, and there's a lot of opportunities for things to go wrong. So here we have a zoom-in version of that part of the passes. A pass in O3DE is an encapsulation of GPU work. Passes can do graphic work like draw stuff, or they can do compute or transfer operations. They can run in different queues. They can share the same command list. And those red lines or those green lines are the focus of this talk. They represent the synchronization that needs to happen between the passes in order for everything to work properly. So I'm going to go through some of the principles, the design principles that were used when building Atom. The first one is that the frame structure needs to be declared beforehand. What is the frame structure? The frame structure means that all the passes, all the resources, all the usages, in which queues are going to be running, how much, an estimation of how much work a pass is going to be doing, all of that needs to be declared at the beginning of the frame. So with that information, we have a full view of everything that's going to happen before we do any actual GPU work. The frame structure change frame to frame needs to be built at the beginning of every frame. The second one is that passes need to declare their structure. In order to do that, in O3DE, you can do it through C++ or a data-driven approach like JSON. So you have all the flexibility of something dynamic in C++ where you can change the type of resources or how you use the resources for a pass, or you can have a more static approach where you have one JSON file that defines the whole pass, and then it doesn't change from frame to frame. We also have the graphic work needs to be inside a pass. We don't allow having any kind of GPU work outside of the passes. And finally, the synchronization happens under the hood. So we don't have any exposed APIs that somebody can call saying, I want to do a layout transition, or I want to like record a barrier, or I want to signal a semaphore or anything like that. All of that happens in the Vulkan API using the information that is provided by the user. So in order to capture the whole frame structure, O3DE uses a data structure that we call the frame graph. Frame graph is a directed acyclical graph that contains all the passes and all the resources that are going to be used during the frame. So this one gives us the full view of the frame, and this is what I talk about the frame structure. The nodes in this graph represents the passes, and the connections between the nodes represent a consumer-producer relationship, meaning that a pass is producing something that another pass is going to be using later. Over here, it's a part of the frame graph that was built from those 50+ passes that I showed you before. So the frame graph goes through 3 different phases in order to produce a frame. So we have the first phase. The first phase, as I said before, is the prepare or the compile. So the prepare or the building is where we grab all that data has written in the JSON file all through C++, and we build these frame graphs that I talked before. Then we have the second phase is where we grab that information and we start creating all the synchronization primitives that are needed in order for the frame graph to be executed properly. This is the phase also that we update all the descriptor set with the proper information. And finally, we have the third phase is the execution, is where the passes are gonna submit their work, and we're gonna grab all those synchronization that we created in the previous stage, and we're also gonna submit it into GPU so everything works properly. The execution works in a parallel way using multiple threads, where every pass can record into a command list, or they can even record to multiple command buffers, depending on how much work they say at the beginning they're going to do. So if we have a pass that say, yeah, I'm going to do a lot of work, we grab that for that pass, and we create a bunch of secondary command buffers, and we give all the secondary buffers to this pass in different threads so they can record their work. So for a pass needs to declare its structure, and part of that is declaring all the resources they're going to be using. This is the key part. So on the left here, we have an example of a pass that we have the inputs, and on the right side, we have the outputs. Inputs on O3DE are treated as read-only resources, and output are read and write resources. So the most important thing that needs to be declared here is the usage. That is how a pass is going to be using a resource. It can be a render attachment, a depth stencil, a copy resource, a shader resource, any kind of stuff like that. You can also define other information like the load store operation that are needed, or if you have any clear operation that needs to happen before running this pass. You can also specify a sub-resource if you're not going to use the full resource during this pass. So over here, I don't know if you can read, but there's a list of all the different uses that are accepted by O3DE. As you can see, those usages map pretty closely to what the Vulkan standard specified. And this is no coincidence because it helps us do this translation easily from a value from the engine to the value that the Vulkan API is expecting. So by tracking these resources by each of the passes, we can start building the frame graph. So in this example, we have 4 passes, and we have pass 1 that is declare resource 1 to be used as a render target. And also we have pass 2 that's also declared that usage of that same resource after pass 1. So there's going to create a connection between pass 1 and pass 2 because pass 1 is producing something that pass 2 is going to be using to do their work. We also have pass 2 that is writing into a buffer, so it's producing another resource that pass 3 and pass 4 are going to be using. So there's a connection between pass 2 and pass 3. But there's no connection between pass 3 and pass 4 because there's no consumer-producer relationship over there. They're just reading from the same resource. So after we create the full frame graph for the frame, we go through all the frame graph and we remove any kind of nodes that are not adding anything, something that was left there. We do a detection of a cycle because the frame graph is an acyclical directed graph. So any kind of cycles that we detect means that the frame graph is invalid. And finally, we do a topological sort where we grab the frame graph and we convert it into an ordered list that is going to give us the execution order. So nodes in that list, so if a node appears first in the list, it means that it's producing something that the other node is going to be consuming. So after we have this sorted list and we have the resources that each pass is going to be using, we move to the compile phase. So in the compile phase is where all the synchronization primitives are going to be generated. These synchronization primitives are going to be stored inside the path, and they're going to be executed or they're going to be submitted in the later phase of the frame graph. So the first synchronization that we're going to generate are variables that are derived directly from the usage that a pass declared. So if a pass says I'm going to use a render target resource X, so that's going to generate a variable for that resource. The pipeline state flag, the access, and the layout, they're all deduced from the usage and the access. Remember, read and write, that they were declared in that JSON file at the beginning. So for image variables, we need to know the current layout of that image. So we keep track of the layout for all of the image sub-resources. Every time we do a transition, every time we create this variable, we keep track of that using an interval map data structure. Another type of synchronization that we do is cross-queue synchronization because passes can run in different queues. For that, we create semaphores that are going to be doing the signal and wait operation in the different when submitting the command buffers. If there's any transfer of ownership because the queues are from different families, we also generate the release barriers and the acquired barriers that are going to be submitted also in the next phase. Since there's transfer of ownership, we also keep track of the ownership of all of the sub-resources the same way that we did it for the image layout. O3DE supports two types of resources, transient and permanent. Transient resources are the resources that they do not outlive the length of a frame, meaning that after the frame finishes, we don't really care about their content. But from the frame graph, we know exactly when a resource is going to start being used and when it ends being used. So after a transient resource finishes being used, we can reuse that same space to create another resource to take advantage of the same space. This is called this is where the aliasing comes. And in order for this to work, we need to generate barriers the first time they're going to use a resource that is being aliased to do the proper synchronization. In the example, we have render target 1 that is going to be used only in pass 1 and pass 2. And we have render target 3 that is only being used in pass 3. So this gives us the opportunity to overlap the same memory for resource 1 and resource 3. This is an example of one of our tools where the green rectangle represents the memory that's going to be being shared. The blue rectangles on the top are all the passes that are running, and the red rectangles represent the resources that are being created. The height of the red rectangle represents how much memory is using, and the width of the red rectangle represents how long that resource is going to be in use. So anything that is in the horizontal axis means that is aliasing memory. As you can see, the top resource, the big one that I think is a depth stencil, is aliasing with all of those small resources that are being used by the passes at the end of the frame. Another barriers that we need to generate are some clear and resolve barriers. Some passes, they need clear operations, and we don't have a render pass to do that. So we need to generate a barrier before we do the clear operation in order to transition some resources and to do the proper synchronization. The same happened for the resolve operation. O3DE supports doing resolve through command buffers. So we need to generate the barrier right before we do the resolve operation. So after we generate all those synchronization, we move to the next step, which is the frame graph execution. So this is the part where passes do the actual recording of their GPU work into the command buffers, along with the synchronization primitive that we generate in the previous step. We do a small optimization of the barrier to reduce the number of barriers that we're going to be recording. So for the optimization, if we have any multiple memory barriers in a pass, we just merge them into one. If for some reason we have barriers that are affecting the same resources, we do the same and we merge them into one. We transform barriers into subpass dependency if possible, but I just heard from the lecture in the morning that they're useless, so I guess we're going to remove that. We also use the initial and final layout when we're creating render paths to do any kind of image transition that were specified through a barrier. We have different stages where we record the barriers that we generated when executing a pass. We have the aliasing stage where we record all the alias barriers. Then we have the clear stage where we record all the clear barriers along with the clear commands. Then we have something that's called the prologue that is run right before the pass execute, and this is where all the resource usage barriers are recorded. Then comes the time for the pass to submit their own work. After they finish, we have what we call the epilogue stage where any kind of barriers that need to happen after the execution of a pass is recorded here. For example, any release of ownership barriers are recorded at this point. And finally, we have the resolve stage where we emit all of the resolve barriers along with the resolve operations. Also, the signal, the semaphores that are going to do the signaling and waiting for the cross synchronization are added to the command buffer when submitting to a queue. So over here, I have a small example trying to explain all of this, the way we execute the barriers and the work. So we have 4 passes and 2 queues. The queues don't belong to the same family, so there has to be a transition of ownership. Pass 1 is going to be using resource 1 as a depth stencil. So the first thing that is going to be doing, we're assuming that that resource is alias. So the first thing it's going to do is going to record an alias variable. Next is going to come the resource usage variable, meaning that it's going to transition that resource into the proper layout, the depth stencil layout. Then comes the turn of pass 2 that is going to be reading from that depth stencil, but as a shader resource. So it's going to record a barrier to transition that resource into a shaded read resource. And it's going to be writing into another buffer resource 2. So it's going to record a barrier for synchronize the access to that resource. At the end of pass 2, is going to come, there's going to be a ownership transfership. So pass 2 is going to record a release barrier for that resource 2. And this semaphore that's going to signal the end of work is going to be added when submitting the command buffer into Q1. Then comes the turn of pass 3. Pass 3 is going to finish the transfer of ownership. So it's going to record a barrier for doing the acquire. And the command buffer for Q2 is going to wait for the semaphore that is going to be signaled by the other command buffer. So pass 3 is going to be read and written for that buffer, resource 2. And then we have pass 4 that is going to be reading also from that same buffer, resource 2. So it's going to record a barrier before it starts that's going to protect and access, do the synchronization for the shading read of resource 2. And it's also going to be writing into buffer resource 3. So it's going to record another barrier to protect the writing access to that resource 3. That's pretty much it. Any questions?
I see hands. Let me transfer microphone. Thanks.
I didn't quite understand. Why exactly do you need clear barriers? Isn't the resources already supposed to be ready for writes or whatever by the time it has to be cleared?
Because the path can declare when you have that file that before using that resource is going to do a clear operation with a specific value. Let's say the path is going to say, hey, I want this resource to be clear with this value before I'm going to start using it. So because of that, we have to create that clear operation. So if it has a render pass, if you have a render pass, we can use the render pass to do that clear. But if it has, for example, is in a buffer and it says, hey, I want to clear with these values before I start working, then we have to do a clear operation for the state.
Okay, it's not just for render targets. Got it.
No, it's not for render. You can specify for different stuff.
Sorry.
Hi, thanks for the talk. So I noticed when you describe the resources that you use in the past in your frame graph, you specify the usage of that resource and the access, and you use that to determine the pipeline stages. But I didn't see you tracking which shader stage it's being used in. So how do you differentiate between resources being used in the vertex shader from resources used in the fragment shader? Without that, it's going to be really difficult to get vertex and fragment overlap, which is really important for performance on tiled architectures.
Yeah, so I have another slide that I added, and basically it's implementing that. We don't track that information. So an optimization that we're trying to do is ask more information to the user, because right now we put all of them because we have no idea if it's going to be vertex, fragment, compute, and other. So we're putting all of them to protect us for the synchronization. So we are going to add a way for the user, when they're creating that pass and they're specifying in usage and read write, there's going to be a section that says, hey, I'm going to be using this shader read in this stage. So you can you only need to protect access in these specific stages.
Great. A second thing is you merge barriers into one, which is generally a good thing to do. But there are cases where merging barriers can actually be a bit dangerous, and you can introduce additional dependencies that you didn't actually mean to. I will be talking about that a bit in my talk tomorrow. So
yeah, that will be interesting to see, because you're right. It could create more problems, or it could actually slow down the execution if you merge the barrier. We're not 100% sure. So if you can enlighten us with your talk, that would be awesome.
Great, thanks.